We now want to take you back from the oceans, back into the mountains. We want to bring you back into the map of the Himalaya Tibet, the importance of the actual geological map for all of the geology and geophysics that we do in the whole mountain belt. It's absolutely amazing to think back that 90 years ago, Argan was already, on the basis of the mapping of the 19th and 20th centuries, early, was understanding that India was underthrusting Asia in a big way. And to get you back there, we've invited a giant of the mapping of the Himalaya Tibet, Mike Searle from Oxford, no connections with MIT, I think. Been up in that mountain, those mountains for more than 30 years. Not only a geologist with great collaboration with especially the isotope dating world, but with the stratigraphers and the paleontologists and everyone else, but also a climber, a mountaineer who's not been afraid to go to the highest parts of the mountains and to produce new maps of Everest and the like. So Mike, we're very glad to have you here. We know that you have been stricken by Vienna. Several of us were in Vienna, have not come back and are half dying, but we realize that you'll probably survive the next 40 minutes or so. And please take the scene and show us your Himalaya.
Thank you very much. Thank you very much, David. I do apologize to start with. I'm on the process of losing my voice. I hope it's going to last for the next 40 minutes, but should I just suddenly go quiet, it means that you just need to look at the slides, because a lot of the writing is on the slides. Okay, well, as David said, I'm going to talk about the geological record with the Himalayas, which is the greatest mountain range on our planet, and one that is very young and actively ongoing. So the two of the major tectonic processes that we're looking at are the lateral extrusion of the Tibetan Plateau, the eastwards extrusion as a result of the Indian collision, first proposed by Molnar and Tapanier many years ago. And the second one is the channel flow model, which is along the crest of the Greater Himalayas. So I'd like to acknowledge some 30 years of friendship with Peter, who's come with us in the field. And I think one of the most impressive things is that Peter climbs mountains and stands on active faults. This is the Karakoram Fault, and he's certainly kept me grounded in his geophysical concepts. So hopefully what I'm going to talk about, the geology, doesn't clash too much with the geophysics. So this is an outline of the talk. I'm going to start off by looking at the Himalaya, the metamorphism, melting, and the channel flow. And then look at Tibet, and particularly the timing of crustal thickening and the uplift of the plateau, what we can infer from the geologic record. And then the strike-slip faults and lateral extrusion. And finally, I'll take a brief look at the Karakoram. So the starting point of all of this is really the India-Asia collision. And you can define it a number of ways. My favorite way of defining it is when the ocean near Tethys finally vanished. And it's at exactly that horizon there. This is a mountain in southern Tibet. And all of these rocks were marine limestones, and they're overlain by this continental molasse. When you collect rocks from the youngest marine sediments, that band there, it is full of nummulites, which belong to the planktonic foraminifera zone P8. And that is the youngest marine sediment exposed anywhere in the Indus Suture zone and on the northern margin of India. And it's particularly known from Waziristan, Ladakh, and southern Tibet. So I take as a ballpark figure 50 million years. This coincides with the decrease in the drift of India after the collision, which we've already heard about, and various stratigraphic units on there. This is what the nummulites look like. They're quite spectacular for fossils. They're about as big as your fingernail. And these fossils are less than 1 million years in their evolutionary cycle. So the oil companies use this all the time in the Middle East for dating, very, very precise dating through the Cenozoic units. A picture taken in Ladakh. This is the main Indus River. Leh is over here. And these are all the rock types you see in the suture zone. Tethyan oceanic sediments, exotic blocks, and these green rocks here are serpentinized hartsbergites and dunites belonging to the remnant ophiolites. There's a few high-pressure rocks and the post-collisional molasse sediments, all of these rocks here. So that marine continental divide is a stratigraphic horizon that is present all over the Zanskar-Ladakh Himalayas, and it's very spectacularly well exposed. So after 50 million years, there was no more Tethys between India and Asia, at least from Waziristan on the western margin of the plate all the way along the Indus Suture Zone in Tibet. The Himalayas are actually a very simple mountain range, unlike the Alps and many of the older ones. There's 3 major units in here, this is Roger Bilham's diagram of the Tethyan upper crust, which is the folded and thrusted sedimentary rocks, dominantly Permian and Mesozoic. The Greater Himalayas, which is all high-grade metamorphic rock, dominantly silimonite and kyanite gneisses and migmatites, and this is what is flowing. And the Lesser Himalayas, which is the old margin of the Indian plate, accreted. So when you restore, in a very simple way, all the thrust sheets in the Himalayas, this is what you end up with. It's one contiguous plate. There is no suture zone along the main central thrust, like some people would like to put. There's not an iota of oceanic rocks or ophiolites or anything. And the one horizon that restores from Lesser Himalayas to Greater Himalayas to the base of the Tethyan is the Proterozoic sequence, the Hymanta group, which is the source for many of the leucogranites that were melting during the Miocene. Here we have a passive margin sequence with the ophiolites on top, and this was the first thing to happen. This happened before the India-Asia collision, probably we think around the late Cretaceous, the same time as all the ophiolites in Oman and along the western part of Pakistan. So to put the model first, here we are. The first effects of the continental collision is a huge thrust sheet of ophiolite thrust onto the passive margin of India. This is equivalent to the Oman stage. TM means Somarari, which is one of the 2 localities of ultra-high pressure metamorphism. And they are Permian units encased in a lot of Paleozoic lower crust material. During either the last stage of ophiolite abduction or the first stage of collision, those rocks, Indian plate margin rocks, were subducted down to anything up to 27 kilobars. This is the only real continental subduction we see anywhere there. And both Somarari and Kagan are very well dated now, which I'll come on to in a minute. During the next stage, the Somarari, the ultra-high pressure rocks, come up extremely rapidly through the mantle until they're ensconced in the lower crust. And at this time, they're caught up in all this incredible isoclinal folding that affects kyanite-grade metamorphism. This is down to 10, 12 kilobars. And I think the real secret for unlocking the crustal structure of the Himalayas lies in these metamorphic rocks, because you can do amazing things with metamorphism nowadays. Pressure, temperature, time paths. You can date monozites at every stage of the PT path. And this is really what's opened my eyes to the thermal evolution. And finally, we have the silimonite cordiorite stage, which is equivalent to the channel flow stage, where all of this is migmatite, and all of it is flowing between 2 enormous great ductile shear zones. Main central thrust below, South Tibetan detachment above. So the first of these are the 2 localities of ultra-high pressure eclogites. They're incredibly fresh rocks. This is right up in the Kohistan region. These were first discovered by Paddy O'Brien, and they've now been extremely well studied by several groups. And in Ladakh, we have another one, the Somarari eclogites, where there has been some reported microdiamonds and ultra-high pressure material, but we don't see pressures anything like these ones up here. It's the Taliban. what we do see is peak pressures of high-grade metamorphism somewhere in this region here, between 22 and 27 kilobars, and extremely rapid rise. You must have some sort of slab break-off. To pull, you have the UHP eclogites in the continental margin. They're dragged down to depth. When the slab breaks off, they come up at extremely rapid plate tectonic rates, and Randy Parrish proved this more than 10 years ago with less than 1 million years between the UHP rocks and some of the lower rocks here. When they get entrained in the base of the crust, in the kyanite grade, they follow a more normal exhumation, which is still fast. It's kyanite grade regional metamorphism. So when, after the India-Asia collision, the rocks start to deform, you are shortening somewhere in the region of 300, 400, 500 kilometers purely in the upper crust. These rocks here, this is in Ladakh. There's probably about 5 kilometers between the mountain tops and the valley bottoms in the Zanskar River. Yellow is just tracing around bedding, and red is thrust fault. And this is all in unmetamorphosed sedimentary rocks, dominantly limestones. So this is how you collide India and Asia, you shorten the crust and you thicken it in the upper crust. And these rocks in the lower crust are going to be converted to kyanite and sillimanite gneisses. Several of us have done a lot of mapping in the Greater Himalayas. Dorji Gruchik in the Bhutan region, and our work in Zanskar, and we both came up with this model, which is essentially exactly the same as channel flow. We didn't call it channel flow at the time, but it's pretty much the same. Now, all of these this is a map of the metamorphic isograds, and it's extremely difficult to make a map of isograds. You're basically looking at the first incoming index minerals: staurolite, kyanite, sillimanite, muscovite, sillimanite K feldspar, and migmatite. To concentrate on the Everest region, where we've been working for the last few years, at the top of the slab is the South Tibetan detachment, this low-angle normal fault, which is spectacularly well exposed on the north side of Everest and all the way along the Rongbuk Valley in Tibet. So this diagram is based on photographs. It's definitely there. So this is a low-angle normal fault putting Ordovician limestone on the summit of Everest over the yellow band, which is an upper green schist, lower amphibolite facies marble. This is staurolite grade schist, and then all of the orange and red are sillimanite, K feldspar, migmatite, and leucogranite. So there is the highest mountain in the world, Everest, has 2 normal faults running through it, one chopping right through the summit there, putting these green schists above the very high-grade gneisses, and on the very top of Everest are Ordovician limestones, which still have some relic fossils in that you can date. This is looking straight up the north face from the Rongbuk side, and a lot of the thin sections of this is a sample of the summit limestone collected by Ed Hillary on the first descent date, 29th of May, 53. And this one collected from the yellow band by the previous attempt by Evans and Bordelon. These are both in Cambridge now, but this clearly is a sedimentary rock, and this is clearly a metamorphic rock, and the boundary between the two is the Chomolungma detachment. Now, beneath the normal faults at the top, there is a section, anything up to 50 kilometers wide, very shallow dipping, which is all in sillimanite grade migmatite up here. So you have an inverted metamorphic sequence along the main central thrust, and actually a right way up sequence along the South Tibetan detached zone, and this huge area in the middle of the slab, which is basically at partial melt temperatures and forming a lot of leucogranites. Not sure what's happened there. Within the slab itself, there are numerous ductile shear zones and thrusts, and what we found from extensive uranium-lead, zircon and monazite dating is that most of the older Himalayan leucogranites, the tourmaline, muscovite, garnet leucogranites, occur in the core of the slab around the south side of Nuptse. These are about 23, 24, and As you go up, the PT conditions decrease, and as you go down towards the main central thrust, they decrease as well, away from this central zone of migmatite. So the boundary conditions for channel flow is that you've got a very thick zone of partially melted rocks in the middle crust. This is not the lower crust, this is purely the middle crust. Sillimanite-grade migmatites, leucogranites, bounded by brittly deforming Tethyan zone above, and a rigid Indian plate lower crust, which is dominantly Archean and Paleoproterozoic, which is unsubductible. So when you restore the whole Himalayas, you must, under thrust, at least the southern part of Tibet, the Archean Indian shield, you must thrust it underneath the plateau in exactly the way that Argand described many years ago. So you have right way up metamorphic sequence along the top, and synchronous motion on both the ductile shear zones, the MCT and the STD. So the results of this crustal thickening, largely because the Hymansa complex, the Proterozoic black shales, are incredibly rich in uranium. These are the protolith rocks that melt when you increase the pressure and temperature to form the leucogranites. And these are the famous Himalayan leucogranites that form most of the big peaks. These are 100% crustal melts. There's no mantle component. There's a local migmatitic source, usually with sillimanite, sometimes with cordierite, at varying stages of the melting process. Incredibly high radiogenic heat production in the middle crust, and the emplacement is along giant multiple Searle complexes, with the uranium-lead ages spanning those 23 to about 16. So they have incredibly high strontium 87-86 ratios, 100% crustal melts, there's no mantle component whatsoever. You can melt a peelite, you can melt a grey-wacky, you can actually melt a cave feldspar algan gneiss to produce these granites. And all the structures in the granites are horizontal sills. So they are isotopically heterogeneous at all stages. They're very famous for containing tourmaline, and the source for the tourmaline is a very boron-rich sediment, probably the Hymansa sediment, released from the breakdown of clay minerals. And these are the classic structures you get with tourmaline quartz schorl. You get exactly the same in the Dartmoor granite in Cornwall, where they're called schorl rocks. The emplacement of these granites is all horizontal. There's no ballooning pluton at all. These are the Himalayan granites in white, and the dark are the sillimanite gneisses. You can see the odd small dikes feeding magma up to higher sills, and great big xenoliths of sillimanite gneiss at the top. But basically, everything is related to horizontal motion in the footwall of the low-angle detachment, the STD. These are the two dehydration melting reactions. The first one is the muscovite dehydration, which produces the standard tourmaline garnet muscovite leucogranite. And a slightly higher temperature one is the biotite dehydration, where you have sillimanite and cordierite, garnet and melt. The stable phase at relatively low pressures is cordierite, and the stable phase above 5 kilobars is garnet. So you have spectacular varieties of leucogranites and migmatites. It's one of the most spectacular parts of the world to study migmatites. These are just a series of beautiful exposures along some of the stream sections south of Manaslu. Typical PT path for these rocks in the channel flow is it crosses the first melting reaction here, which produces what we call the normal type granites, garnet tourmaline muscovite granites, and at very lower pressures, more cordierite bearing granites. Most of the top of, this is the largest area of the late cordierite granites. The entire top of Makalu is fed by this sill. This is on the Barron Glacier on the southern side of Nepal. And this, you can see that the cordierite granites here feeding the summit are actually cutting all the earlier tourmaline 2 mica granites on the margins of the dike. This is just an outcrop to show you the spectacular deformation. This is one boulder, literally the size of that carpet. And it has 7 different phases of cross-cutting granite. And pretty much these granites are coming in at relatively low temperatures, and then they freeze pretty instantly. to produce all of these. And we've been doing uranium-lead age dating on all of these different phases, and they vary both spatially and with depth as well. So this is on the Kangshung Glacier on the north side of Everest, where we have, this is in the core of the channel, when the whole melt is being extruded out to the south, and within that are giant boulders. It's almost like a river with giant boulders of these migmatite, sillimanite gneisses and earlier formed leucogranites. And our students, John Cottle and Micah Jessup, did a lot of work dating these rocks. And what John found in particular was that there is a southward younging of ages. So here you see the spectacular early sills, which are folded, cut by undeformed set-to dikes. And you can date these, and the time periods of deformation are spectacularly short-lived across all of this stuff. So what we found in the Rongbuk Valley is one of the best sections, because you have this 3D exposure from the summit of Everest till the STD plunges down beneath the Tibetan Plateau, and you can follow it along strike for the whole period. And a summary diagram here shows all of John's uranium-lead ages at the Kangshung. This is in the guts of Everest. And this is Thongmong, which is right in the northern tip of the GHS before you go underneath the Tibetan Plateau. So we think that there is a general northerly younging trend with time along the Rongbuk. This is on the south side of the Nepalese Himalayas, a spectacular cliff section showing Amadablan. This is just south of Everest. Anyone who's trekked up there would have seen this peak. And when you look very closely at this, you can see that these granites are intruding as layer parallel sills with dikes feeding magma up to the top. And the reason they're bending over to the north is because the STD is up here and cutting through the Everest Massif off to the left. So this is a summary diagram of the ages of the STD. And what we did was try to restore this section. There's absolutely no way you can restore a ductilely deformed channel of migmatites, but what you can do is use the pressures to constrain roughly the depth, and if you assume that the STD is the same angle during the formation, then you've got to bring these leucogranites from this period here about 100 kilometers north of where they are now at the foot of Everest. So that's the Ordovician limestone, that's the yellow band and the green schist facies rocks, and this is all migmatite down here. So this is a summary of the Himalayan thermal history. You have collision at 50 million years. From then, post-collisional crustal shortening. We don't know how much. It's absolutely impossible to restore sections through the GHS, so I wouldn't frankly believe any of these balanced cross-sections across the entire Himalayas. You can restore the Tethyan zone above, and you can restore the lesser Himalayas, but there's no way you can restore the ductilely extruding middle crust of the greater Himalayan sequence. What we do know is that the syn-collisional eclogites are forming pretty much at the same time as collision. And we have exactly the same rocks in Oman, so I suspect that these, the very deep subduction of the leading margin of India, are actually the final stage of the ophiolite abduction rather than the collision. And then we have the kyanite-grade collision, which is dated between 35 and 30, and the sillimanite-grade partial melting between 24 and 15, producing these spectacular leucogranites. So this was the time of channel flow. Channel flow is not operating today. It's seismically dead. There is nothing happening on the STD or the MCT. The seismic boundary is way down to the south along the main boundary thrust. Well, this is the Annapurna section. Dhaulagiri is up here. This is all Cambrian Ordovician limestone at the base of the Tethyan sequence. And all of this is sillimanite and kyanite-grade partial melting with the famous inverted metamorphic sequence on the main central thrust. So you have a low-angle normal fault here, which is responsible for extruding the magma in the footwall. Low-angle normal faults do definitively exist, and they must have been active at low angles in order to exhume this stuff during the channel flow. I think there is no evidence that Tibet or the Himalayas are collapsing, so I don't like the orogenic collapse story. Normal faults do exist. In Tibet, they're oriented north-south, east-west extension, but because of India, the lower crust of India, the Archean Paleoproterozoic is underthrusting it. It is just jacking it up and jacking it up. And everywhere you see the greater Himalayas, there is no evidence of anything falling down or collapsing. So here is a picture of that same normal fault. On the hanging wall, we have Cambrian limestones of the Annapurna Formation. And here we have, this is all calc mylonites dominantly, produced from the Cambrian limestones. And immediately underneath it, huge amounts of marble at high temperatures and kyanite gneisses with partial melt. So there's a massive PT jump across this ductile shear zone. Again, if you play the same restoration games, this is what you see now. There's 3 rocks here. The sediments at the base of the Dhaulagiri, which are purely burial metamorphism, anything up to about 2 kilobars, 2.5 kilobars. The tremolite gneisses from the Langtang units here, and the kyanite migmatites down here. And if you use the pressures to constrain the depth, you have to restore them to this sort of position. And then you're bringing this one up to accrete with this, and then both of these up to accrete with that. All of this leads to channel flow. And everything on the right-hand side of the diagram here is constrained by the in-depth and the high climb experiments, geophysics. Once you cross north of the Indus Suture zone, you don't have the depth constraints. What you do have in the Himalayas is spectacular depth constraints as you go north. So we know that this is the basic geometry of the mid-crustal channel. And what is thrusting down underneath it is dominantly Archean and Paleoproterozoic, which could be forming in eclogite facies down here, depending on who you like to believe. So putting together all the uranium-lead ages, most of the melting, the crustal melting, which triggers channel flow, is happening up here, generally between about 25 and 16. And as soon as you run out of melt, that stuff just flows. As soon as you start melting it, it just flows out to the surface, and you had incredibly rapid PTT paths, exhumation of these rocks from relatively shallow mid-crustal levels. So this is the channel flow model, which I like very much. I think it fits all the geology, the PT work, and we even have constraints on the lower crust. These high-pressure granulites in southern Tibet, there happen to be some spectacular Shoshonite and Adakite dikes that intrude up through all of this, and they're ripping off bits of the upper mantle and bits of the lowermost crust. And when you see that, this is one of these Shoshonite dikes intruding at 12.7 million years in southern Tibet. It is full of xenoliths, tiny little xenoliths, about that big. And these are both mafic and felsic granulites at extremely high temperatures and high pressures. They also have zircons and monazites, which you can date. So we absolutely know that at 15, 16 million years ago, the crust underneath southern Tibet was extremely thick and extremely hot. So here's a summary of all of the Everest PTT work. I'm going to skip along pretty quickly here, actually. And as I said, the Himalayas are very pretty much uniform, the whole length of the mountain belt. They've undergone the very similar kyanite and sillimanite grade events, except for the very far northwest in Nanga Parbat and the very far northeast in Namche Bawa, the 2 syntaxes areas. And in this region of Nanga Parbat, it is quite some of the most incredible rocks I've ever seen. Most of the core of Nanga Parbat here is composed of extremely high-grade migmatite. And when we have dated these migmatites, Jim Crowley and Sam Bowring were collaborating on the dating. These are the cordiorite-bearing leucogranites that are intruding up extensional shear zones here. And these big green things are cordiorite, and there's tourmaline, garnet, muscovite. Some of the ages are actually less than 1 million year old. So we're looking here at rocks that have been exhumed from about 3.5, 4 kilobars in 700,000 years. And that is a phenomenal exhumation rate. There's nowhere else in the world that is exhumed as high as that. This is the outcrop that David G. was talking about, where the Precambrian gneisses of Nanga Parbat, metamorphosed during the Miocene and the Pleistocene, are thrust over practically unconsolidated gravels of the Indus River. So these rocks in Nanga Parbat have been through the whole cycle. Apart from all the early Precambrian and Cambrian collisional events, they've been through the high-pressure eclogites, which still occur in parts of Nanga Parbat. They've been through a major kyanite event and a widespread sillimanite event and a very young sillimanite cordierite event. So I think they're pretty good representative of metamorphism that is actually forming today underneath parts of the Himalayas. Okay, well, Tibet, as everyone knows from all of Peter's work, Tibet is the largest exposed area of high elevation and thick crust in the world, and some of the big debates are when did the plateau rise? This is most of the geophysics constrained from the in-depth experiments and the high climb and the earlier Owens and Zant. Most of these models show that the southern half of Tibet up until about the Pangong Suture Zone was under thrust by cold Indian mantle lithosphere. We don't know exactly when, but what we do know is that the plateau are absolutely covered by these post-collisional Shoshonites and Adikites, and these are spectacular rocks that Shoshonites come out of the mantle, and Adikites come from a garnet-rich eclogite or garnet amphibolite source, and they are present all over the plateau. Sun Ling Chung from Taiwan has spent 20 years working on these rocks and dating them, and he's come up with a spectacular, I think, time-space diagram. This is India going north across the plateau, and these ages are constrained by the distribution of Tibetan magnetism. And the story basically is that as India is shunting northwards, under thrusting Tibet, it is progressively moving the hot Asian mantle northwards. So now, in the last 10 million years or so, the only young Shoshonitic volcanism occurs up in the Kunlun in the far north, but in the central Changtang belt and in the Karakoram, it basically went on pretty much from collision onwards. So putting all this together, here's a model of what we think the Tibetan crust could look like in southern Tibet. All of this, felsic granulites, mafic granulites, ultramafic restites, and eclogites are constrained by the xenoliths coming up the Shoshonites. The Shoshonites are coming up from the mantle, plucking off bits of this lower crust as they come up. Most of this is old pre-collisional Gangdesi-type granites, and the Adikites you have to melt from something like a garnet-bearing lower crustal source. Oh, sorry, seen that. Okay, well, this is a spectacular outcrop. I'm sure anyone who's been to Tibet has seen this. Paul Kapp has done a lot of work on here. What we can know is that there is a major unconformity that is regional across the whole of the Lhasa block. And this is below the Lingzizong volcanics at 60 million years ago. All of this folding must therefore have occurred prior to the India-Eurasia collision. We also know that the youngest marine sediments anywhere in the Lhasa block are about 130 million years down here beneath the Takina red beds. So from 130 million years, Tibet has got to be above sea level. Now, what is happening with the eastern margin of Tibet is a big problem, because this is Wiki and Marion Clark's model of lower crustal flow, and this is the active GPS. I think there is no way that you can relate the GPS, which is purely a superficial deformation, to anything that's happening in the middle and lower crust. We know that the upper, middle, and lower crust are completely detached all through southern Tibet. We've been doing a lot of work in the last 2 years on the Gongga-Shan granites. This is the Shanshui-He fault, one of the most active faults in Tibet. There was a paper by Roger et al. With a very young zircon age, that's why we went there. But actually about 80% or more of this batholith is old pre-collisional hornblende biotite granodiorite. Most of this goes back to the Indo-Sinian, and it is not applicable to crustal melting like we see in the Himalayas. So there's actually huge amounts of variety in the Gongoshan granite. Most of this batholith is pretty inaccessible, but there are two very good road transects that go up here. And these are all the early dioritic rocks. So we can summarize most of the metamorphism in eastern Tibet, particularly from Damba, is all Indo-Sinian. There's no Cenozoic metamorphism at all. There's nothing young. Everything is either Precambrian or Indo-Sinian. There is no geological evidence for crustal flow. In the Himalayas, there's abundant geological evidence for the greater Himalayas thrusting to the south. You never see that along the eastern margin of Tibet. And all of the granites are dominantly related to the Triassic, Jurassic, Indo-Sinian orogeny. The other major problem is the faults, the strike-slip faults in Tibet. This is the Karakoram Fault, where Peter and I have been several trips. We've had incredible discussions with our French colleagues going on for about 2 decades on this fault. And for me, it's very clear that all of these migmatites and granites are related to the regional metamorphism you see all across the Baltoro. They are absolutely nothing to do with shear heating on the fault. The fault cuts everything. The youngest granites in the Karakoram are as young as about 10, and the fault must have been initiated prior to that. Some of the ductile fabrics on these outcrops, this is Richard Phillips, who's published a lot, my student, and it does have a major difference in exhumation rates on either side of it. It also has spectacular pseudo-tacholites. The fault is pretty much dead now. There's almost no seismicity on it. But it does show huge amounts of pseudo-tacholite, which you don't really see on the Shanshui-He fault. Well, I've mapped all of this part of the Karakoram. You can't go to this region here. It's right on the triple junction of Pakistan, India, and China. But that contact there is this one. It's a contact metamorphic aureole between the 20 million year old Baltoro granite and carboniferous black shale. It's very, very clear, black and white. You can trace that with a dashed line to intersect with the Karakoram Fault there. And on the other side, on the Ladakhi side at the top of the Siachen Glacier, that same contact is very clear there. That is about 25 kilometers. This is the most active fault in Tibet, and it seems to have just a minimal amount of motion on it. It's quite extraordinary. So we think the Karakoram Fault actually accommodates about 120 kilometers maximum, could be as little as 25, since about 15 million years. The metamorphism and the granite intrusion all occurred before strike-slip shearing. Leucogranite dikes are synkinematic with the ductile shearing, but none of them cross-cut the brittle faulting. In fact, the ages of the metamorphism there are exactly like we see in Pakistan. They're late Cretaceous. And the fault is pretty much seismically dead today. So either it's moving with huge amounts of recurrence time, or something very strange is going on. But I don't think the Karakoram Fault has been solved by any means. The Altintag Fault, again, these rates are reasonably well constrained. The GPS rates are extremely well constrained. I'm not sure I believe these rates very much, but we don't know what the total geological offset on the Altintag is. The Karakoram in North Pakistan is actually equivalent to the Changtang block in central Tibet. And these rocks here give us, most of the Karakoram is composed of high-grade metamorphic rocks and granites. All this stuff here with an enormous batholith in the middle, the Baltoro crustal melt batholith. So these rocks give us some indication of what could be going on underneath the central part of Tibet today. And when we've done an enormous amount of uranium-lead dating, most of this is done with Randy Parrish. There's a whole bunch of pre-collisional dioritic-type gneisses related to the Andean margin, and an enormous number of peaking post-collisional metamorphic ages, culminating in this time here when most of the Baltoro granite was intruded. At the same time, you have lamprified dikes coming out of the mantle, and I think the sheer volume of granite in the Karakoram is indicative that you've got to have some amount of mantle heating. It's not like the Himalayas at all, which have almost no mantle component to this. The crux of the Trango Towers, this is a one-to-one cross-section. There's no vertical exaggeration. These things are 2 or 3 kilometers vertically, and most of that batholith is between 17 and 18 million years. So you can summarize all this in a time chart, and India-Asia collision, 50 million years. All of these sillimanite gneisses and migmatites are occurring in an Andean-type setting prior to the collision of India and Asia. And then you have everything in blue is a period of peak sillimanite or kyanite metamorphism, dated with monozites and extremely well constrained. And what you see is a pretty much continuous record of high-grade metamorphism throughout not only the post-collision, but also some of the pre-collision. And this, I think, could be indicative of what's going on under parts of the Changtang block. We're moving around the corner a bit, and I'm working now in Burma, in the Mogok Belt, and these rocks here have a very similar uranium-lead history to the eastern Himalayan syntaxis. So we're sort of tracing the Lhasa block, the southern margin of Tibet, around the bend, into Burma and eventually down into Thailand, and restoring it with the various time constraints that we have. Here's a model that was published by my student Richard Palin, who did a lot of spectacular uranium-lead age dating on all of these granites. And we think now that the thick crust and the was actually inherent there from at least 45 million years ago. You cannot have kyanite and sillimanite grade metamorphic rocks without having some sort of thick crust. You cannot quantify it. We have no idea how high the Karakoram was. We have no idea how high Tibet was. But what we can say is that when you've got a period of high-grade metamorphism, you've got to have some sort of thick crust. And if you've got thick crust, you've got to have some sort of topography. So the conclusions of Tibetan Karakoram, thick crust, high elevation, I think was a pre-collisional event along the south. The Gangdesi geology is exactly the geology that you see all the way along the Peru-Chile margin. Huge I-type granite batholiths, huge amounts of calc-alkaline volcanic rocks. I don't think the plateau rose 7-8 million years ago. I think it's been around for a long time, older than that. There is no real evidence for mantle delamination. Looking at the ultrapotassic Shoshanite ages, they were occurring all the way from 45 up to day before yesterday up in the Kunlun. The strike-slip faults are very large scale and impressive, but they have very limited offset. And we still don't really know the offsets on most of the Tibetan strike-slip faults. The earthquakes are restricted to the seismogenic zone. Some of the excuse me. Some of these deep earthquakes underneath the Himalayas, lots of arguments between the creme brulee people and the jelly sandwich people. I personally cannot see how you can have temperatures as low enough to make an earthquake in the mantle. So to me, this has to be, the crust is deeper and thicker than we think it is. Anything up to 90 kilometers deep. Post-collisional crustal melts are very rare, but there's 3 areas, the Ulug Mustak, where PISA has also worked, and the Western Nianshan Tangla, little bits of crustal melt leucogranite, and these little tiny, very young granites in Gongoshan, 4 or 5 million years old. What they result from is anybody's guess, and that is a real problem that we haven't yet solved by any stretch of the imagination. So to conclude, the timescales of orogeny, the ophiolite abduction phase onto a passive margin, pre-collision, is extremely well tied down in Oman. The northern margin of India went through all of this with the ophiolites along the southern margin of Khoistan. the Spontang ophiolite and most of the ophiolites, the good Ganser ophiolites under Tibet. Himalayan-type collision, it's 50 million years of deformation, 50 million years of metamorphism, and it's still ongoing. Karakoram-type metamorphism includes the pre-collisional and the post-collisional, and that is absolutely huge. It's been going on pretty much peaking for 65 million years throughout the pre- and the post-collisional phases. So in conclusion, I'd like to pay my respects to Emil R. Gand, who 90 years ago, I think, got it dead right. The Himalayas is composed entirely of Proterozoic and younger rocks. You never see Archean or Paleoproterozoic rocks in the major part of the Himalayas. That stuff is detached, and the Himalayas are shortened, we don't know, but by several hundred kilometers. The only place you can put the lower crust that restores underneath that is by shoving it underneath the Tibetan Plateau. So I think that was an incredible piece of insight, and I would also like to pay my compliments to Peter Molnar for doing 30 years of spectacular work along there, for keeping me very firmly in my place when I come up with models that are a bit wild, and it's been a great pleasure to work with you. Thank you very much, Peter.